In this video, I'm going to teach you how to write net ionic dissociation equations with our precipitation reactions. If you don't remember precipitation reactions, I would advise you to go back to our reactions unit and look at the notes where we were predicting products. That's where you'll see the precipitation reactions I'm talking about. Now let's spend just a little bit of time looking at some of these words. Ionic dissociation equation. So ionic, we will be focusing on ionic compounds in this video. So remember what ionic compounds are made up of. We have cations and anions, right? So cations are positively charged atom, anions are negatively charged atoms. So you will need to remember the oxidation numbers. And then the word dissociation. So dissociation has to do with the separation of ions. So we're still talking about solutions here. So we talked about in our previous video when a solute dissolves into a solvent, if it's an ionic compound, then there's 100% dissociation. Whereas covalent molecules, when you dissolve that in water, there is no dissociation. Here are your learning targets. Now, we learned about precipitation reactions when we talked about double replacement reactions. So when we have two ionic compounds and we mix them together, sometimes you'll get a precipitate, right? And remember what a precipitate is. A precipitate is an insoluble solid, right? And you saw this as like it was almost like a murky kind of substance. Sometimes it changed colors. Sometimes it was just like this white cloudy substance, right? And that's what a precipitation reaction is. So we can predict the precipitate from our solubility rules, and we looked at a table like this or a chart like this, right? And so just to remind you, on the top half of this chart are our soluble ionic compounds. So anything containing nitrates, acetate, chloride, bromide, iodide, and sulfate, these are soluble. But remember, on the right side of the chart, these are exceptions. So nitrate and acetate don't have any exceptions. They're all soluble. Whereas chloride, bromide, and iodide, if these anions are a compound of silver, mercury, or lead, then they will be insoluble and a precipitate will form, right? So remember, insoluble means a precipitate forms, and precipitate is a solid substance, okay? Sulfate, exceptions are compounds of strontium, barium, mercury, and lead. And then on the bottom half of the chart, these are all insoluble, so anything that containing sulfide, carbonate, phosphate, and hydroxide are all insoluble. But again, on the right side, these are your exceptions. So everything with sulfide is insoluble except for ammonium sulfide, any alkali metal cations with sulfide, and calcium, strontium, barium. So these over here would all be soluble, right? So real quick, is sodium nitrate soluble in water? We look at nitrate. It's all soluble. There's no exceptions. So yes, it is soluble in water, meaning that no precipitate will form. Is lead 2 bromide soluble in water? Well, let's find bromide. Here it is. Is lead an exception? Yes, it is. So this is insoluble and a precipitate will form. Lastly, magnesium sulfide, is that soluble in water? So again, here's sulfide. Is magnesium a part of one of these exceptions? No, it's not. It's not an alkali metal. It's an alkaline earth metal. And no, it is insoluble. So again, a precipitate will form. Okay. So in order to show a precipitation reaction, there are three types of equations that we can write. The first one is a molecular equation, and that is basically the overall reaction that we worked on during our reactions unit, and it shows all the physical states of each of the substances. So remember that solid, liquid, gas, and aqueous. So aqueous means it is in solution. So a solute is dissolved in a solvent. A lot of times, like copper 2 sulfate, Solution is copper 2 sulfate solute that's dissolved in water, and that's our solution, so that's aqueous. So aqueous is different from liquid. Okay, so liquid substance is a pure substance, like H2O. H2O is liquid. It's a pure liquid substance. Okay, whereas aqueous, again, it's a solute dissolved into a solvent. It's a solution that we're talking about. The second equation would be a complete ionic equation, and that shows each of the aqueous compounds as separate ions. So we practiced this in our previous video when we were talking about our compounds dissociating. So in this, we're going to see all the aqueous compounds dissociate, so we're going to see all the ions separate. The insoluble substances are not separated. And we are going to write this insoluble substance, the precipitate, as a solid. So we're going to write the symbol S next to it. And again, that does not separate. Water also does not separate, so it just has a L written next to it. It's a liquid. And then you're going to see that there are the same ions on both reactant and product side. And those we're just going to cancel out because they don't react, and they're known as the spectator ions, so we just eliminate them. And then whatever remains is our net ionic equation. So let's jump into our example. So manganese 2 chloride and ammonium carbonate react to form manganese 2 carbonate and ammonium chloride. So we are going to write our molecular equation, which is our overall equation first. In order to do this, you have to remember your oxidation numbers, you have to remember how to write ionic compounds, right? So if you don't remember how to do that, I would suggest you going back to our previous unit or previous units and going over your notes. So manganese 2 chloride, we have Mn2 plus, chloride is Cl minus 1, and when we put that together, we need 1 manganese and 2 chlorines to write MnCl2. Next one is ammonium carbonate. Ammonium is NH4 plus 1. Carbonate is CO3 2 minus. You need you need 2 ammoniums and 1 carbonate, and you'll make NH42CO3. Manganese 2 carbonate. We have Mn2 plus. We have CO3 2 minus. You need 1 of each to make MnCO3. And then lastly, ammonium chloride, we have NH4 plus 1, chlorine 1 minus, and 1 of each, so it's NH4Cl. Now, before I balance it, or you can go ahead and balance it first, I'm going to go ahead and write the state symbols next to them. So if you don't remember, for this double replacement reaction, the first two are always in solution, so we're going to write AQ next to it for aqueous. And then for our product, we need to go ahead and figure out, well, are both of these soluble? Will they just be aqueous? Will they be in solution? Or will one of them precipitate out? So in order to figure that out, we're going to have to go back to our chart. So looking at our chart, which one will precipitate out? Is it manganese 2 carbonate or ammonium chloride? So let's look. Chlorides are all soluble except for silver, mercury, and lead. So ammonium is not part of those exceptions. So ammonium chloride is soluble. Let's take a look at manganese 2 carbonate. So here's carbonate. All this carbonates are insoluble except for compounds of ammonium and any alkali metal cations, and manganese is not one of those. So therefore, manganese 2 carbonate is our insoluble compound. So we are going to show our precipitate as a solid. So next to the manganese 2 carbonate, we're going to go ahead and write a solid symbol. And then ammonium chloride is soluble, so we are going to write aqueous for that. Next, we're going to balance it. I need a coefficient of 2 in front of my ammonium chloride, and that's it. So let's now write our complete ionic equation. So in order to do this, we are going to split up, or we're going to write the ions for each of my ionic compounds that are aqueous. Okay, so solid, we're not going to do that. That's just going to stay together. That's our precipitate. It doesn't dissociate into ions. So if we look here, and you can refer back up to here, right, our scratch work up here. Manganese 2 chloride, when it dissociates, it will form Mn2 plus ion and a chlorine ion. Okay, I'm going to come back afterwards and deal with the total number of atoms here to make it match my ions here. But right now, I just want to focus on writing out all of my ions. So Mn2 plus and chlorine, or Cl minus 1. And then now let's take a look at ammonium carbonate. So when that dissociates, we have NH4 1 plus and CO3 2 minus. And manganese 2 carbonate, again, we're going to leave alone because that's a solid substance, so that does not dissociate. So I'm just going to write that as is, MnCO3 solid. And then my next substance, ammonium, NH4 plus 1, and then chlorine minus 1. So there are my ions. Now, I'm going to go back and go ahead and match up the number of atoms with the ions. So here I have one manganese. Here I have 2 chlorine, so I'm going to put a 2 in front to represent that there are 2 chlorine ions. Okay? Ammonium, here I have 2 ammoniums, so again here I'm going to write 2. Carbonate is 1, so I'm going to leave that alone. Skip MnCO3. And we're going to come to ammonium chloride. That coefficient distributes to each ion, so there are 2 ammoniums and then also 2 chlorines. Okay? Before we move on, I want to go ahead and write the state symbols next to each ion. So all of these are aqueous. So I'm going to do that here with my complete ionic equation. So you're going to notice the ions, some of these ions are the same, and those ions are the spectator ions. So they have nothing to do with the net ionic equation. So we're going to go ahead and cancel or cross those out. So we have the chloride ion and the ammonium ion. Those are our spectator ions. And the net ionic equation is whatever's left over. So we have Mn2 plus and then carbonate ion, and it'll give us our precipitate, manganese 2 carbonate. Okay. If we look at our next example, we have the reaction of potassium chloride and lead 2 nitrate. So in this one, I'm not telling you the product because I want you to actually practice predicting the product, okay? So if we write our reactants, and you can pause the video at any time. So I want you to go ahead and write the ionic compounds for potassium chloride, or the formulas, sorry, for potassium chloride and lead 2 nitrate. So potassium chloride is KCl, and lead 2 nitrate is PbNO3 So this is a double replacement reaction. All of these are going to be double replacement reactions. So do you remember how to predict your product? Remember, it's the inside that will pair up, and then the outside that will pair up, right? So in this case, one of the products will be lead 2 chloride, and another one will be potassium nitrate. Okay, so again, just like we did before, though, you have to consider the oxidation numbers. So just like how I showed you how to write it down, the scratch work, I would suggest that. So here's our molecular equation, and we want to go ahead and write the symbols next to each substance. So again, the reactants are both aqueous, but you need to figure out which one of the product is your insoluble substance so that you can write it with a solid for precipitate, right? So go ahead and look back to your solubility chart and figure out which one will precipitate out. So you just said that lead 2 chloride is the one that precipitates out, so that's why I have the solid symbol there. And then I'm going to balance it before I move on. And I need 2 in front of the potassium chloride and 2 in front of the potassium nitrate. Now let's go ahead and write the complete ionic equation. So again, the first thing you want to do is just go through and write the ions. Do not worry about the coefficients. Do not worry about matching up the number of atoms to the number of ions, okay? Just go through and write all of the ions that all of our aqueous substances will dissociate into, okay? And again, your precipitate you leave alone. That will not dissociate, so you're going to write that as one entire substance. All right, so now you want to go through and make sure that our ions are balanced, so meaning our ions match up the atoms from our overall molecular equation. So potassium, here we have a coefficient of 2, so we need 2 potassiums here, and again 2 chloride ions there. Lead, we're good. Nitrate, here's our 2, so we need 2 nitrates there. Potassium, there's a coefficient of 2, so 2 and 2, and we're done. Okay, we're going to go ahead and write everything in aqueous form there and cross out our spectator ions. And then whatever is remaining will be our net ionic equation. And no, it does not matter how you want to write this. Pb2 plus can be first. I just wrote it exactly how I saw it in my complete ionic equation. All right, so go ahead and pause the video and try the next 2 problems on your own. When you're ready to check your answer, go ahead and unpause and play through the rest of the video. So the second problem that you have here is sodium carbonate and iron 2 chloride. And the products will be iron 2 carbonate with sodium chloride. So you should have that, and then figure out which one will precipitate out, which is your iron 2 carbonate, and balance, and then let's write the complete ionic equation. So we have sodium ion, carbonate ion, iron 2 plus, chloride ion, sodium ion, chloride ion, and then again our precipitate does not dissociate, right? Got to make sure that we have the same amount of ions from our original molecular equation. So here we have Na2, meaning 2 sodium, so we got to put a 2 in front. Carbonate is 1 and 1. Iron is 1, leave that alone. Chlorine is 2, so we need a 2 for our chloride ion. 2 NaCl, that means each sodium ion and chlorine ion get 2 in front. And then cross out your spectator ions. And then whatever is remaining is your net ionic equation. Barium nitrate and ammonium phosphate. Our products will be barium phosphate and ammonium nitrate. And again, remember to look at your oxidation numbers all over again when you're writing your new products. Let's go ahead and figure out which one will precipitate out. That's your barium phosphate, and let's balance. Okay, 3, 2, 1, 6 are our coefficients. And then complete ionic equation, we have barium ion, nitrate ion, ammonium ion, and the phosphate ion. Our precipitate is all together. We have our ammonium ion and nitrate ion. Let's go ahead and make sure our coefficients match up. So here we have 3 barium, so we need a 3 here. And then here we have 3 times 2, so that's a total of 6 nitrates. Okay. Here, ammonium, we have 2 times 3, so that's 6. And then phosphate, we have 2, so we need a 2 in front. Okay. Over here, 6 ammonium, so 6 right there, 6 nitrates, and so 6 right there. Go ahead and write your symbols, your state symbols, cross out spectator ions, and write your remaining as your net ionic equation. And that is how you write your complete net ionic dissociation equations.